Great. So for today, we scheduled a training on the Wi-Fi design. So Wi-Fi is generally a topic for itself. When we are speaking about wireless communication and implementation of access points and optimizing the Wi-Fi network, it's not that straightforward and obvious like when we speak about wired network. Because of that, we need to understand really how Wi-Fi works in order to be able to identify potential problems which we can have with the Wi-Fi signal. So first of all, let's start from the foundation. What is the advantage of the wireless and why we go to wireless at all? First of all, to point out that we never can have that reliable, low latency connection through wireless like we have on wires. So we go on wired connection as much as we can. So all connections between switches and the router, all backbone connections, they are on wire. Wireless is just alternative when there is no any other choice and we have to wirelessly bridge certain distance. Also, why wireless is still that popular is because in modern network with modern devices, it's not feasible to expect that end user would have their phones, tablets wired all the time. So because of the mobility, today's end user devices are almost completely connected to the Wi-Fi and the wireless. So when we speak about wireless connection, we typically speak about connection of end devices to the main network and the devices which are directly showing the user interface and which interact with the end user. So generally the Wi-Fi, the main advantage of the Wi-Fi is it provides mobility and also it provides in theory unlimited number of connections, because with the wired connections we are limited with the number of the ports on the switch. Of course, in practice we cannot use unlimited number of devices on a single access point, but generally there is no physical connector which limits how many devices we can connect on the access point. So those are two advantages which keep wireless that popular: mobility and scalability, to say like that. So what wireless communication is in fact? So any kind of a wireless data transmission is based on electromagnetic waves, and electromagnetic waves are different based on the wavelength and frequency. As a relation between wavelength and frequency is always constant, it is light of speed. We can each electromagnetic wave we can describe as a length of the wavelength or as a number of the frequency. Typically, for describing the Wi-Fi communication, we use frequency, and Wi-Fi is operating on two main frequency bands, 2.4 and 5 gigahertz. Today, we also have additional band recently introduced, which is 6 gigahertz, but in Araknis, we still don't support that band, so I will not speak much about that. In the frequency spectrum, the part where Wi-Fi operates is somewhere between microwaves up to infrared waves. So the reserved part for the Wi-Fi is just a small part of the total frequency spectrum, which we use for electromagnetic transmissions. Main frequencies used on the Wi-Fi are firstly introduced 2.4 gigahertz and 5 gigahertz. So what are the benefits of having Wi-Fi communication done on the higher frequencies? Higher frequencies means more data throughput, and also it brings more energy through the electromagnetic waves. Because as you can see here, when we look at the wavelength, we have much more transitions from low to high voltage level with high frequencies than with the low frequencies. That practically provides us that we transmit more information for the same amount of time with higher frequency transmission. So if we have more data available on 5 GHz, why wouldn't we always use 5 GHz in that case? So downside of the 5 GHz frequency band is that the coverage area is much smaller. So it tends to decrease faster comparing to 2.4 GHz. So generally, it is much more affordable to have this certain area covered with 2.4 gigahertz access points than with 5, because to cover same area, we would need more access points if we would like to have full area covered with 5 gigahertz. But 5 gigahertz generally is much better when speed of transmission is in question, and also when interference is in question, but I will speak about that in details later. So first of all, without going into too much technical details about the Wi-Fi, first what we need to know about setting up the wireless is that it is critical from security point of view. Sorry.
Don't worry.
Okay, I think that someone said something, no worries. So what is critical from security point of view when we are speak about Wi-Fi is accessibility to the Wi-Fi network. As I mentioned previously, the main advantage of the Wi-Fi is easy access and mobility. And because of that, anyone can enter Wi-Fi network as soon as they can discover on mobile phone, they can connect to it. So for that reason, first, what we do when we are setting up the Wi-Fi, we need to protect our Wi-Fi from unauthorized access. So each Wi-Fi network is identified by its name, which is called SSID. So each SSID represents one Wi-Fi network. And for each SSID, we can define the way how the end device authenticates to join our wireless network. The easiest way, of course, and the least recommended way is to leave just Wi-Fi network open. That means as soon as wireless device identify the Wi-Fi, it will automatically connect. And that is something what we definitely want to avoid. And we always have to have a certain level of authentication required for end devices to connect. So typically what we use like a short password. So only the end users with knowledge of the password are able to connect to our network. In history, practically the way how that authentication done is developed to be more and more secured. Currently, the latest accepted protocol for authentication on the Wi-Fi is WPA3 SAE, and it is implemented on our Wi-Fi 6 access points or X20 access point. But I would say that still, in general, the Wi-Fi authentication, which is the most commonly implemented, is WPA2. WPA2 is, let's say, generation behind WPA3, and as it is older protocol, it is less secure to WPA3. So what we always tend to do is to have the security of our wireless network on the highest possible level. So we would use WPA3 whenever is possible. But what can be a problem if we limit our network just to support WPA3? Some legacy wireless devices, they simply cannot recognize new protocol. They can work only up to WPA2. So if we lock our network to accept only WPA3, some old devices maybe wouldn't be able to negotiate and wouldn't be able to connect. So I would say that the best option in that case would be to use WPA3 mixed, which means the access points first tries to authenticate using the latest security protocol, and if device is not supporting that, it decreases to previous one to WPA2. Okay, so beside this, the PSK, which means pre-shared key authentication, where you use password to connect. There is also one additional way to register, to authenticate with the wireless network, and it is so-called enterprise or server-based authentication. In that case, access points, when receives requests to authenticate wireless user, it always communicates with the server, typically Radius server, to check the database of username and passwords, and to verify it and send to allow access to the end user. It is most commonly used in commercial environment, and typically what we use on Araknis is so-called pre-shared key, where all users are using the same password to connect to the wireless network. So the most important thing is to remember that when you connect your access point, by default, Wi-Fi will be enabled and open, so anyone can join it. So first, what we need to do when we switch it on, we need to protect it with the password so we can prevent any unauthorized access. Okay, so let's go next. The second thing, which is also quite straightforward, and we do not need any additional knowledge of wireless technology, is so-called guest network, which is also available as an option on the access points. So what is the difference between the guest SSID or guest wireless network comparing to the standard SSID? The main difference is that all devices connected to guest SSID are completely isolated from the rest of the local network, and they have access only to internet, nothing else on the local network. So even without any knowledge of IP addressing, firewall rules, access lists, you can easily, just by enabling guest network, completely isolate devices on your local network and provide them only internet access. So it is quite commonly, it is quite common feature on all the access points. How it works? So generally, when you enable guest SSID, access point acts as a router for those devices. Access points assigns IP addresses, and access point generally do NAT of those addresses of the end devices to the IP address of access point itself, and it is forwarded directly to the internet. It's not allowed to go anywhere else in the local network. So those are two main options which needed to be done right with initial setup. To lock the SSID from open to WPA3, recommendable, and to enable guest SSID for all devices which shouldn't have access to the local area network. Okay, so let's see now in more details what is behind Wi-Fi and how Wi-Fi operates. So first of all, we need to know what channels we have available in each Wi-Fi frequency band. So first, on the 2.4 gigahertz, we have typically 11 channels available to select from. The number of channels is different from region to region. It can be from 11 to 13, but typically it is 11. And the width of each channel which we use for transmission is 22 megahertz. As we have 11 channel in the quite narrow frequency band, that means that only 3 channels we have in 2.4 GHz, which are completely non-overlapping. Why it is important that channels over which we communicate on the Wi-Fi are non-overlapping? Because if we use neighboring channels which overlaps some part of the frequencies, one channel sees the other channel as interference, as a noise, and it directly affects the transmission of the data. So in ideal situation, all channel will be completely separate and there will not have any kind of overlapping for the clear data transmission. So typically, as you can see on this diagram, we use channels 1, 6, and 11 because those 3 channels do not overlap one with each other. And we have only 3 non-overlapping channels on 2.4 gigahertz. Typical mistake, what I see on the field is that installers, they put simply all the access points, and when I say all the access points on the same network, on the same channel, because the way how they see it is that access points, in order to operate in the best possible way, they all should use same channel. And that is not true, because access points, even if they are from the same network, from the same project, they represent interference front for each other if they are on the same if they are on the same frequency. So even the access points in the same network, they always should use different channels. So in short, one access point should be surrounded by access points which are all using different channels comparing to the access point which is reference point. That way, we have the best possible transmission on the Wi-Fi. So let's check how channels on 5 GHz look like. As you can see here, 5 GHz frequency band is much wider comparing to the 2.4 GHz. The channel width, minimum channel width on the 5 GHz band is 20 megahertz. And that means that all channels on the 5 GHz band are non-overlapping. So we do not need to think like on 2.4, what channels are overlapping and what are not overlapping. Every channel has separate frequency, not non-overlapping with other channel on 5 GHz. So we can use any channel on 5 GHz. Also, what is additional option on 5 GHz, which doesn't exist on 2.4, are so-called DFS channel, dynamic frequency spectrum, which are used only if there is no any other device emitting in that range. Typically, this range from channel 52 up to 144 can be used from the radars. And if access points detects any activity on those channels, it will jump from that channel to some non-DFS channel to avoid collision on those channels. So generally, if we have enough free channels of 5 GHz, we will not use DFS. But in situations where we have quite congested environment, even on 5 GHz, we can enable DFS as an option, but just we need to have in mind that at any moment when there is some collision on DFS channel, access point will jump and potentially break the transmission at that moment in order to avoid collision with the radar signal and things like that. So DFS channels are useful option when we don't have enough free channels on the 5 GHz, but in general, we don't use it. Yes, Tabitha.
One question. How do you know, or what tool do you use to know if there's any radar or something in the DFS channels?
So you should use some kind of Wi-Fi frequency analyzer in order to detect how that frequency spectrum looks like in that area. When that is in question, in order to have like a professional level of site survey, definitely would be need some third-party application, like typically what we recommend is MetaGeek with its own Wi-Fi adapter, and it is able to completely show you the frequency map on the certain area and to detect what signals are there. But just to know, if we do site survey at certain moment and if it is free, that doesn't mean it will be always free. It can happen that that signal jumps in and cause the signal to get out. So it is good. It is good practice maybe just to know, are there any potential sources of, is there any radar in close, or are there any potential sources or interference there? Because they are not always constantly present. Maybe at the time when we are doing site survey, they will not be detected, which doesn't mean that some moment they can appear. Just to know, because I had experience with the customers where projects are configured, Wi-Fi is configured to use DFS channels, and the connection at some moment simply drops, and they were not sure what's going on. So just to know, if you are using DFS channels, because of that option that it can jump by itself, if there is a collision, connection can drop. So you can expect that with the DFS channel is used. If you don't use DFS channels, that should never happen. Okay, so what we saw so far is that 2.4 gigahertz frequency band has much narrow frequency range with only 3 overlapping channels, while on 5 gigahertz we have all non-overlapping channels there when we use 20 megahertz. But now the situation gets a little bit more complicated, because on 5 gigahertz we typically change the channel width. So why we would change the channel width on the 5 gigahertz? Simply because with wider channel width, we provide more throughput. We provide more bandwidth on the wireless. But at the other hand, if we have wider channel, we have less non-overlapping channels available. So if we go from 20 megahertz to 40 megahertz, our number of non-overlapping channels are cut by half. If we use even 80 megahertz, we have only 4 non-overlapping channels that we had with 20 megahertz. Also, just to mention, we have this option only also on 2.4 gigahertz. We can use 40 megahertz channel width, but it is always never used because 2.4 megahertz, 2.4 gigahertz band is narrow enough that there is no much sense to use wider channels, because you will have much more problems with interference. But as a 5 gigahertz band is more clear comparing to the interference from the outside, there is a sense to use wider channels, because in general we don't have that amount of interference like on 2.4. Just what we need to take care of is that if we are using, for example, 80 megahertz with central frequency of 42, that means that 80 megahertz channel width is overlapping with all channels 36, 40, 44, and 48. They are all one channel in that case. So we shouldn't use that channel on the neighboring access points. Also, we have, with the latest Wi-Fi 6, we have option for 160 megahertz even channel width. So you can imagine in that case what range of channels it covers, and we are quite limited then what channels are free, which are not overlapping in that case. But just remember, typically with 20 megahertz 5 gigahertz channel, all channels are non-overlapping. How we increase the channel width, we increase the bandwidth, we increase the throughput, but we also decrease the number of non-overlapping channels. So we always need to think what channels are overlapping or not in that case. Okay, so this is like quick comparison between 2.4 and 5 gigahertz. Just to summarize, 2.4 gigahertz has only 3 non-overlapping channels, and when I say when I'm speaking about non-overlapping channels, I mean channels with 20 megahertz channel width. Can you hear me?
Yes, we
Okay.
can.
Okay. So when I'm speaking about non-overlapping channels, I'm speaking about the standard 20 megahertz channel width. On 2.4 we have 3. On 5 gigahertz, all of channels are non-overlapping. 2.4 gigahertz has lower throughput. 5 gigahertz has higher throughput. But 2.4 gigahertz has better coverage comparing to 5 gigahertz, which has less coverage with the same transmit power. So that means if you would like to have the same area covered with the Wi-Fi, only on 5, we need more access points, which means more expensive solution. Okay, so let's see what is interference. Now, when we know how Wi-Fi operates in terms of channels, let's see how we can design our channels to work the best. So first of all, we different types of interference. First of all, it is co-channel interference. What I mentioned before, if we have two access points operating on the same channel, they are noise one for each other. So they should definitely be on different channel. Also, we have adjacent channel interference, which means if channels are just partially overlapping, for example, channel 1 and channel 3 on 2.4 gigahertz, they will also cause interference. So they should be completely non-overlapping in order to be interference-free. And also we have non-Wi-Fi interference coming from devices which are emitting signals on 2.4 gigahertz, which are like baby monitors or microwaves and things like that. When I speak about non-Wi-Fi interference, 2.4 gigahertz band is by far the worst band for interference because really a lot of devices are operating in that band. So 5 gigahertz for that reason is much better solution because it's more interference free comparing to 2.4 gigahertz. And when we speak about attenuation, just to mention that the signal level from the access points, it is decreased by distance, and it decreases really fast. It is proportional to the square of the distance. So it drops how distance rises really fast, exponentially. And also the other reason why we have attenuation of the signal is, of course, some obstacles, especially like concrete wall, which are cutting the signal significantly, and behind the wall you have much attenuated signal. So those are two main reasons which can affect the quality of the Wi-Fi signal: interference, and distance or obstacle in the Wi-Fi transmission. So the Wi-Fi is not the only protocol which operates on 2.4 gigahertz. We also have on our controllers, on our Control 4 controllers, additional protocol, wireless protocol called Zigbee, which also operates on 2.4 gigahertz. The channels on how they are marked on the Zigbee and on Wi-Fi are not the same channels, just to remember that. Channels on Zigbee start from 11 and go to 25. And on 2.4 gigahertz on Wi-Fi, they go from 1 to 11. How they overlap, you can see on this diagram. And definitely the Zigbee is source of interference for Wi-Fi, like if we have additional access points on the same channel. So They operate in the same frequencies, and they represent noise one for each other. For that reason, we need, when we design the Wi-Fi, we need to take into consideration any Zigbee signal as well. And if we use the standard scheme 1611 on the Wi-Fi, we should choose channels 15 and 20 on Zigbee, because as you can see on the diagram, they are between channels 1 and 6 and 6 and 11. So they are interference free when Wi-Fi is in question. And also there is one additional channel which is out of Wi-Fi occupied frequencies, and that is channel 25. But channel 25 should be our last resort, because as you can see on the diagram, the signal strength on the channel 25 is slightly lower comparing to other channels, which means it has lower coverage. So always go on with channels 15 and 20, and only if there is no other choice, channel 25. Okay, so I mentioned that there is, besides interference on the Wi-Fi itself, sources of the interference which are non-Wi-Fi related. It is, of course, rogue wireless access points from different, for neighboring house or for neighboring apartments, microwave, cordless phones, they also operate at 2.4, Bluetooth devices. Some bad electrical connections can also cause some electromagnetic emission on 2.5 gigahertz, Zigbee, radar. When I say radar, I think on DFS range on 5 gigahertz, sensors, wireless video cameras, etc. So in general, any device which is working on the same frequency as your Wi-Fi signal is affecting quality of your transmission. So the main point is to have clear channel where no one else is operating on the same frequency. Okay, so that is I would say the most important and the hardest parameter to set on the Wi-Fi in order to have reliable connection. The second parameter, which is quite important, is transmit power. Typically, when we speak about the transmit power, we would think maybe that more power we have, more stable connection we have. But that's not the case. There is optimal value of transmit power for each position of the access point. So of course it is obvious why it is better to have a low signal, because that way we simply don't have coverage in certain areas. But also equally bad is if we have too strong signal from multiple access points in the same area as well. So the main idea is to have the site designed that way that it at any point in the house, at any place, we have dominant access point to connect to. That is the main idea. What is, of course, tightly related to the transmit power is radiation pattern. When radiation pattern is in question, all our access points are omnidirectional. So there is not much to make wrong there. Wherever you locate it, it will simply emit the signal all around. But there are slight difference, as you can see, from plane to plane. There are slight difference in the radiation pattern. So for that reason, we always say that the recommended way how you position your access point and how your access point should be oriented is from the front face to the down. So the best way is to place access point in ceiling, and it is going setting beam directly down to the floor. But generally, as you can see, it is more or less omnidirectional. So here on this, the X plane, you can see that the gain is the highest directly from the access point to the front. Just to point out, when we speak about the access points and the radiation pattern, all antennas are integrated within the access point. So you don't have external connection to connect any different antenna, maybe directional antenna. The radiation pattern is depending on the antenna type. So we have integrated omnidirectional antenna, and this is the only way how access points can be used. With access points where you have external antenna connector, you can use directional antenna and that way change the radiation pattern for certain access points. In this case, everything is integrated and you always have omnidirectional. With preference to have a radiation beam going directly from the front face of the access point. Okay, so how we measure is signal strength good enough or not with Wi-Fi? The parameter which we use to estimate the quality of the Wi-Fi signal is called RSSI, the Received Signal Strength Indicator, which in fact represents the ratio of the useful signal comparing to the floor noise. It is always a negative value, which means the lower the number is, the better the signal is in that case. Everything which is above minus 65 dBm is good quality signal, providing reliable connection and high throughput. When we go below minus 65 dBm, we are still in that functional area, to say like that, all the way up to minus 70 dBm. But below minus 70 dBm, we still, of course, can connect and receive the signal, but that signal can already start to have suboptimal performance when bandwidth and speed is in question. What definitely is not acceptable as level of RSSI are any signal which is below minus 80. So when we are doing some design and we are doing the site survey, if you would like to avoid some third-party Wi-Fi, definitely we should look to place access points on some positions where surrounding Wi-Fi signal is below minus 80 or minus 90 or something like that, because those level of signals are really non-functional, to say like that. So just remember that even if you have really poor connection, like minus 8 or even minus 90, that doesn't mean that you cannot connect. You will be able to connect, but your connection would break really fast. Your speed will be really bad. You will have a lot of lost packets. So the fact that you are connected doesn't mean that your signal is good. Signal ideally should be better than minus 65. Okay, so when we talk about the strength transmit level, we don't take into consideration that in the real-time scenario there will be definitely some obstacles. Any measurement which is done based on the coverage and expected RSSI on certain distance are done in ideal environment without any obstacles in place. What is significantly affecting our wireless signal are, of course, walls and anything through which signals should go. So in this table, you can see example how much different material is affecting our wireless signal. So first of all, we have glass window, which is from 2 dBm, then wood 3 dBm, cubicles 3 to 5 dBm, etc., etc. And the worst are glass with a metal frame 6 dBm, brick 8 dBm, and concrete 10 to 15 dBm. So, for example, if we have signal at 65 from one side of the concrete wall, on the other side it will have a level of -80, which, if you remember, I mentioned it is unacceptable level of the Wi-Fi signal. So in those cases where we have like a lot of concrete walls, small rooms with concrete walls, the best Wi-Fi design would not rely to transmission of one access point on both sides of the wall. In that case, the best would be to have one access point per room, just to be sure that signal is always on acceptable level. Okay, so why it is important that we have a strong signal in each part of the house? Because the signal strength is directly affecting the achievable speed on the Wi-Fi transmission. The typical question I get is why end customer cannot achieve the speed which is in specification of the access point. It's never possible to achieve that speed because that is theoretical maximum speed for protocols supported on the access point, which is latest now, which we support, is Wi-Fi 6 AX, 802.11 AX, in ideal conditions. So always count that in practice it is around 60-70% of that as maximum achievable speed. So what is affecting speed on the Wi-Fi transmission? There are really a lot of different factors affecting that, and this diagram is explaining why the measured speed is always much different comparing to advertised speed, which is in the specification of the access point. First of all, it is up to limitation to the end device. If my access point supports Wi-Fi 6 and 802.11ax protocol, that doesn't necessarily mean that my end device supports that. Maybe my end device simply doesn't recognize that protocol and cannot push those speeds. Also, what is quite common problem there is that access points has, for example, 4x4 antenna arrays, and it is able to multiply bandwidth using the multiple antenna arrays, which end device is not able to do. It has just 2x2 or things like that. Then second thing is limitation when radio interface is in question. I explained before that 5 GHz provides much better speed comparing to 2.4. So if I have certain area covered only with 2.4, my maximum speed would be around 3 times lower comparing to the speed which I would have if I've connected to 5 GHz. This is also something I hear quite often from the field, that end customer experience when they walk through the house, they experience significant drop in the speed when going from one part of the house to the another. Typically, that is because their phone switched from 5 to 2.4. Because in order to have more cost-effective network, typically network is designed that way that we have coverage, completely covered house with 2.4, while on 5 GHz we have coverage gaps. When customer is in those areas with those gaps, it can connect only to 2.4 and speed significantly drops in that case. Also, what is definitely affecting the speed is the number of streams coming from the certain device. Of course, more streams, more parallel streams you have, connected to the access points, more bandwidth you have available. Channel bonding. When I say channel bonding here, I mean on channel width. Wider channel width means more throughput, more narrow channel width, less throughput, but less interference in that case. And that is when all those elements are counted down, then we go from advertised to nominal throughput. And that is the maximum theoretical throughput in clean environment with the end devices we have on place. So that is something what we cannot affect by changing the position, by changing the location of the access point. It's simply it is like it is using the interference optimal interference setup and optimal transmit power. So from nominal throughput, we then have all the factors related specific to the site, like is there any wireless congestion, how far are we from access point, is there any third-party interference, is there any legacy devices, because it can happen that if we have legacy device, it simply pushes access point to transmit on the lowest protocol like 802.11b or something like that. Are there any retransmits because of poor connection, etc., etc. And when we decrease that part also, which are site related, we come to the effective throughput which we get on the site, which is measured by the end customer. So as you can see, with Wi-Fi, it is a long journey from the advertised to the effective throughput, and there are really a lot of different parameters which are affecting the speed. So because of all of that, we always need to be really careful when we advertise to the end customer what speed, what throughput they can expect from certain access points. Any questions maybe related to that? I hope it is clear enough. So I would go back on my first slide when I speak about this. What is difference between wired and wireless? With wire, you just plug wire on one place, on the other place, and you have that declared speed, like 1 gigabit, 100 megabit, and that's it. You don't have anything what would significantly affect transmission through the wire. With wireless, it's completely different. As you can see, you can never be close to the maximum speed which that protocol implemented in the access point can support.
Sorry, I have
Yes.
a question before we go further. The first one is when you talk about the guest SSID,
Yes.
you're talking about the guest that the Araknis access point itself provides, right?
Yes. Yes.
If we have more than one access point, this option is not optimal, right? Because you switch from one router to another and
Correct. That means each time when device changes access point, it is changing its DHCP server, and it is negotiating IP address from the beginning, like going from one router to the another. That is correct. But in practice, that shouldn't significantly affect the performance. If Wi-Fi coverage is good, that should happen really fast. But generally, that is not optimal solution, because simply guest Wi-Fi is not designed to have that smooth roaming like the standard SSID. From that reason, switching from one router to the another.
Okay, and the other question is in when we are choosing the 20 megahertz or 40 megahertz or 80 megahertz and the channels that we use in overseas in Wi-Fi management, when we try to select the different channels, they doesn't change its name. I mean, for example, there is a channel that is
okay, let me open the Wi-Fi management, and you can tell me what you see. Okay, so let's go to access point.
Yes,
Okay,
for
80
example, this.
megahertz. Okay.
Okay, here.
Mhm,
With 80 megahertz,
mhm.
in the slide that you showed us, 36 is not the one that we can choose. Is
Aha. Okay, so on slide, when you select the wider channel, it uses channel for to represent that wider channel. It used the central channel in the middle of that wide channel. So it was like 42 in that case. But here, in fact, whatever channel you choose, it will combine those four, in fact.
so with 80, it combines. So I can choose whether 36, 40, 44, 48 is the same.
Yeah, so it is always combining the same channels in that case, because it is combining channels which are available for the merging, to say like that.
Okay, good.
So
This is the
36 and 40 will always go. We always use 36 and 40. 44 and 48 for 40 megahertz, for example. We use 44 and 48, and if you use 80, that all four here.
okay. Okay.
So you have
Perfect.
you can say like you have predefined groups, like 4 channels which can be grouped here, 4 channels which can be grouped here, and you can make like first and second as 2, third and fourth as second 2. So it is how it works.
Okay, perfect.
Yeah,
Now it's
it
clear.
is important to remember, if I have like 40 channel here and I use 80 megahertz, all those channels are occupied. I shouldn't use them.
Yeah.
But my central channel is like 42, right? Yeah.
Yes,
Okay.
perfect. Yes, all clear.
Okay.
Thank you.
No worries. Okay, so this covers, in fact, the explanation and potential challenges with 2 main parameters when we are setting the Wi-Fi: channel selection, that means to avoid interference, and the transmit power, when we want to make optimal coverage and reliable connection to the Wi-Fi. So let's go now through the procedure of setting up the Wi-Fi, what we should do. So first of all, for the Wi-Fi setup, we need to estimate the number of the switch ports. That means we need to know how many access points we have in the place. And also, as all access points are PoE, just to point out that Wi-Fi, all X10, Wi-Fi 5 access points are PoE, and Wi-Fi 6, X20 access points are PoE+. We need to design the power budget on the access point just to be sure that our access points would provide enough PoE power to have all access points working effectively. And we need to consider where those access points would be located. And it is, I believe this is quite straightforward. Access points ideally should be in ceiling and on some central position, so all parts of the room or all parts of this area which should be covered by one access points are equally covered, with no obstacles ideally. And what is the worst possible case where you can put your access points is, of course, some metal constructions, racks, or basement. So those areas should be definitely avoided. So next thing, what we need to know is what is the number of access points. Typically, and in most of the cases, the coverage is the main parameter which is affecting the number of access points needed in place. So that means we need to design our project that way that there is no any areas with the coverage gaps which are not covered at all. And also at the same time, we shouldn't put too many access points to have some areas where 2 access points are struggling over same device. If you remember, I was speaking about RSSI and optimal signal level there. So everything above minus 65 dBm is considered a good signal. So we should always stand that our minimum signal in each part of the house should be around minus 67 to minus 70 dBm. In between of two access points. That means if I move from one side or the another from that area, my signal strength to closest access points should be stronger than that, and signal strength from the access points from which I'm going off should be lower than minus 70 or minus 67. So that should be the minimum value in between. And based on that, we estimate the number of access points when coverage is in question. You have two options there. You can do this coverage estimation based on 2.4, where you would need less access points to cover the same area, or if you would like to be sure that you have full 5 gigahertz coverage, we do that coverage survey based on 5 gigahertz only. And in that case, if we fully cover our area with 5 gigahertz and we have a lot of access points, in that case, we can simply switch off our 2.4 gigahertz if we are sure that there are no devices which are working only on 2.4 gigahertz, of course. But that is just one of the approach for the estimation of the number of access points. And typically in residential environment, that is the parameter which is main in estimation coverage. But also there is another parameter which is capacity. When I speak about capacity, I mean on how many end devices, wireless clients, access points can handle at the same time. There is no like hard-coded maximum number of accepted connection from the end devices. So theoretically, you can have unlimited number of devices connected to single access points, but system should always be designed that way that you should avoid having more than around maybe 30, maximum 40 devices connected to single access point. So in some commercial environment where you have a lot of people at a small area, like some halls and things like that, definitely the capacity, the number of users per access point should be more critical than the coverage. And in that case, we are estimating a number of access points based on the number of users which are estimated to be on that area. So if I have like 100 people there, I would place there at least 3 access points. Even when area is in question, 1 access point would be enough. Just if we are designing Wi-Fi based on the capacity, we need to take care about transmit power and overlapping. So definitely those 3 access points, as they are close one to each other, they shouldn't have too high transmit power enabled on them to prevent overlapping between them. So we call that design microcell. But in general, in residential areas, we always do estimation and design based on the coverage. Capacity is more for commercial. Okay, regarding the placement, I already mentioned that when I was speaking about the radiation pattern. Access points are omnidirectional, but the best place to put them in order to use the maximum from the radiation pattern built in is in ceiling. So Wi-Fi beam goes directly to the floor. So troubleshooting, when we speak about troubleshooting on the Wi-Fi, as Wi-Fi is invisible medium, it's really hard to identify the problem. So on this picture, for example, you can see a comparison between wired and wireless network. How looks like good wired network and bad wired network, and how it looks good wireless and bad wireless network. So when we have wires, it is obvious where we have some breakage, some bad cabling or bad connectors. But when we have wireless, those two pictures are completely the same. We do not know what's going on because wireless is invisible. So for that reason, we need to have some software tools which will help us to see what the problems are in the place. So the software tools used for optimizing the Wi-Fi channel selection are typically like MetaGeek softwares for the site survey. And the best practice would be, if possible, before Wi-Fi design is completely determined, to make like one reference point, put one access point, and walk around the house with the laptop and see how Wi-Fi signal is changed from one position to the another. And also that way we can identify the sources of the third-party interference as well. So only with a site survey tool, we can make visible potential problem in our Wi-Fi frequency spectrum. It's not that easy like when we have wired networks. It's not that obvious. When we speak about estimated coverage of one access point, this is really a rough estimation, but we say to have like around 150 square meters open space is area which can one access point cover without any problems with optimal signal strength. That means minus 67 maybe and above. That doesn't mean that within 150 square meters we have visibility of Wi-Fi. We have visibility on minus 80, minus 90 on maybe 30, 40 meters away from Wi-Fi access points. But what we consider with a good and reliable signal is within 150 square meters from the access point without any obstacles. But as I said, we shouldn't rely too much on this estimation because each site is different. Each site is designed for itself. So the best way to exactly know what are potential problems on the Wi-Fi transmission is to do site survey with laptop and do like a frequency scanner around the house to see potential Wi-Fi signal gaps. And if everything is done properly, that means that our transmission and channel selection will provide a clear channel for Wi-Fi transmit, and that will result in the high throughput. As close as possible as to the advertised throughput. That means nominal throughput of the access point. So those are some tools which you can use for the site survey. For Windows, it is Insider or Channelizer, which is more advanced. For Mac, Wi-Fi Explorer, and on phones, Android Wi-Fi Analyzer, Net Analyzer, and iOS Airport Utility. So when we are speaking about Wi-Fi design, we have to rely on software tools, definitely. Okay, so that is related to the channel selection and to the optimization of the throughput. But let's see what is also quite important thing is how our access points overlaps when the signal strength is in question. So first of all, when interference is in question, I mentioned that before, we always should have different channels around our access points. In this case, this is designed for 2.4 gigahertz. And as you can see, for example, on the left cell, it works on channel 6. So neighboring channels should be 11 and 1. And that way, for each neighboring access points, they should be surrounded with non-overlapping channels, 1, 6, and 1, and 1, 6, and 11. The same way how they shouldn't overlap on channel in frequencies, they shouldn't overlap in the transmit power. Optimal transmit power overlap should be between 10 and 15%, which is really, really small. And as I mentioned previously, the signal level in between of the access points should be around -67 up to -70. That means we have optimal overlapping, and we avoid that way the areas where Wi-Fi device is struggling to choose to which access point to connect because it receives too high signal from both access points at the same time. This is most commonly the problem because installers, they tend just simply to put the maximum power on all access points and expect it will work the best. It's not, of course, always the best solution. Each installation, each position has its optimal signal level for the access point. Regarding the comparison between 2.4 and 5, if we use both frequency bands, which is in most cases it is the way how it is done. Just remember that 5 GHz on the same signal level has less coverage. So in order to have same coverage for 5 and 2.4 GHz, to have the same Wi-Fi cell for both frequencies, we need to always put signal level on 5 GHz slightly higher comparing to 2.4. It is around I believe 4 to 5 dBm higher. That way, we are sure that signal level at the edge of the Wi-Fi cell is the same for 5 and 2.4. And if this setup is done properly, if we have optimal signal strength on neighboring access points and optimal channel selection, the result would be that when moving from one access point to the another, we would not have any disconnection or any interruption in the signal, and we would have seamless roaming. Of course, seamless roaming is not that important when we are surfing the net or when we are downloading something, but it is really, really critical thing when we do Wi-Fi calling, for example, or when we are streaming something, because real-time traffic is really sensitive to the latency and to package drop, so it is immediately visible in that case. So in order to have reliable Wi-Fi network to provide smooth transition even for real-time traffic, we need to follow these guidelines to have smooth roaming between access points. Okay, so those are the main things to consider when setting the access points placement, transmit power, channel selection, etc. But also there are some more advanced features available for each access point, which are available also on Araknis access points. First of all, that is band steering. What band steering does, it is in fact overlapping 2.4 and 5 GHz on one SSID with preference to 5 GHz. We do not recommend that much this option because that means in areas where you don't have good 5 GHz coverage, access point can still force connection to 5 GHz, even if on that spot maybe 2.4 GHz would be more optimal connection. So we do not recommend using band steering. And if you have requirement to both 2.4 and 5 GHz SSID are with the same name and to appear as one SSID, you still can do that just by putting the same name on both 2.4 and 5 without band steering enabled. So they will appear as one, but it will not force 5 GHz. Further on, it is fast roaming. Fast roaming improves the it decreases the time needed for end device to negotiate authentication when switching from one access point to the another. Generally, in residential environment, it shouldn't be that critical to be enabled, but I got feedback that even with standard pre-shared key password authentication, it helps a lot when going from one access points to another. But what is the main purpose of this fast roaming protocol is when you have enterprise level authentication, when access points need to speak with radio server. It shortened that time when exchanging the username database between the access point itself instead of reaching to radio server every time. So that way it improves transition time from one access point to the another. But generally, enabling this fast roaming option shouldn't have any side effects, so you can use it in residential as well. Further option is client isolation. Client isolation is more like security security feature. That means any device connected to SSID with this option enabled would have not access to any other device on the same network. Something similar to guest network. Just in this case, they cannot even see devices on the same SSID connected. So it is completely isolated and having just internet access. Furthermore, it is client limit. As I mentioned before, by default, there is no hard-coded number of wireless clients connected to the single access point, but you can strictly deny to have more users connected than it is optimal. For example, you can say on access point, it can handle just 30 devices at a time, and 31st devices would be simply rejected. And at the end, the RTS CTS threshold, this is really advanced option, rarely used. I've never seen it, to be honest, used on the installation. So it is used in the situation when you have a really congested environment and you need to reduce collision by fragmenting the packets sent to the access points. And so that way, in congested environment, the access points is able to handle packets coming from the end user handle more smaller packets, and that way be more effective than if it needs to handle one big packet from the end user, and it spares the time, to say like that, and reduces number of drop packets. Okay, so just let's see how access points are configured. First of all, just to point out that, as you know, we are moving more and more from direct web interface on the access points and moving everything to OVRC. So use OVRC and management tool as much as you can. We have all our access points completely compatible with OVRC and integrated. Currently, we have multiple models available. We have one outdoor 520 on the Wi-Fi 6 series and two indoor 820 and 520 access point. They are all PoE plus access points. And also we introduced recently new entry-level low-cost 320 access point, which is also Wi-Fi 6. But what is different with this access point is that this access point doesn't have 2.5 gigabit on LAN interface. That means it is limited to maximum 1 gigabit speeds because that is limitation on the wired connector on the access point, but the price is much more affordable comparing, for example, to 520, which is also 2x2 access point Wi-Fi 6, but with 2.5 gigabit interface. So 320 access point, something what is intended to be used as entry-level access point, like a light 520 access point. Regarding the advantages of Wi-Fi 6 comparing to Wi-Fi 5, first of all, speeds and throughputs, because 802.11ax protocol is supported. They accept 320, they have 2.5 gigabit Ethernet port, they are PoE plus, improved from the hardware point, they have improved thermal design and antenna design, high power, new cable bay, you have like a plastic for the cable coming into the access point. And when mounting is in question, the ceiling mount bracket is completely the same with as X20, so you can easily just remove X10 and put X20 without need to remove the mounting bracket itself. They also support multiple users and multiple inputs, multiple outputs. That means if you have multiple users connected at the same time, each user has its own dedicated beam to connect, and that improves general throughput across the project. Okay, so I mentioned for the troubleshooting, you definitely have to have some kind of Wi-Fi spectrum analyzer. Those third-party software solutions, they can be quite expensive, but also what I personally use, it is a trial-free version of Insider, and even that trial version, light version, it provides a lot of information to you. This is a live overview of the network in our office. So here you can see all of the information related to currently active networks in this environment. And you also have diagram where you can see overlapping on 2.4 and 5 gigahertz as well. Also, when you select one of the SSID, you can get more detailed information how signal strength is changed during time, and you can see what channel is currently used, what is the channel width, what protocols are in use, and what rates are supported. That means what throughput is supported. Also, you can have here like overview of the occupation utilization of each of the channel. So you can easily estimate what channel should be used on a certain spot and what channels in general should be avoided. You have the same for 2.4 and 5 gigahertz. They are both on this list. I can select certain SSID and get more detailed information about it as well. And also here in the diagram, it's quite useful because you have graphical representation of the occupied channels as well. So you can see that here in office we have quite congested environment on 2.4. So luckily I'm sitting just next to my access point, so I don't have any problem with that. Okay. And yeah, just to point out, this is just like an entry-level version of the site survey tool. If you need more information like deep packet inspection and traffic analysis, you can buy the licensed version and get a MetaGeek adapter for it. But as you can see, you really get a lot of information just with this. When we speak about site survey, we also have site survey built in within our access points, and it is available directly from the OVRC. So let me go back here. So in Wi-Fi management, I suppose you are familiar with this, so I will not talk much about that. In Wi-Fi management, you have overview of all Wi-Fi clients connected with access points where they are connected, and you have a list of all SSIDs used, and you can simply, with a single setup, you can apply, for example, a new SSID to all access points at once in your project. So you have control per SSID level and apply it to all access points in project. And also you have control on the access point level for the parameters which are access point specific, like the wireless mode, that means like optimal protocol to use, channel selection, channel width, and transmit power. Also here you have option to run site survey directly from OVRC, where you, even without any third-party software, you can see a list of occupied channels and what access points are transmitting at that moment, on the what are detected on the spot where access point is located from where you are doing site survey. So just to point out regarding channel selection, of course, you have option for auto configuration. Just have in mind that auto is selecting the best channel at the moment when you install the access point, but that can be changed in time. So if you have some interference problems, even if it is on auto, that doesn't necessarily mean that at that certain moment it is optimal channel selected. So you can always manually go and fix it to certain channels so you are sure what channel is used on certain place in the house. One more remark regarding the site survey. Site survey on 5 GHz is currently working as it should. I'll show you now how it shows the list of 5 GHz SSIDs. It needs some time to scan all. So this is how it looks like. You see the signal strength, you see the MAC address of access points from where it is coming, the channel utilization, all important information you would need when you are selecting the channel. That is on 5 GHz. On 2.5 GHz, currently we have a bug, so it's not showing anything, but we are working on to resolving that. So just to know that at the moment when 2.4 GHz is in question, you have to rely to the third-party software, but 5 can be fully operated from the oversea. Okay, so that is all I prepared for today. Do you have any question for me?
Yeah, Alec.
Fabrice.
Yes, 2 remarks. Sorry, I have some calls from partners, so
No worries.
maybe you already answered to it. The first remark is if you would just go down here, you will have the country. You can
Okay,
that, yeah?
country code, okay.
Yeah. And the thing is, I found that when we change the country by other things than United States, we have
For
some
example,
issues.
France, okay.
Yeah.
Okay, what kind of issue? I can double check. Is there anything reported? So let me.
I didn't check recently, but I remember to get this problem with partner who changed it because it seems relevant to do it, you know.
Okay.
And
everything seems that it is applied, but what happens after?
Device didn't connect it yet. Again, after applying the settings.
So it's completely refusing
the
any
only
connection.
Way, the only way to get the installation back was to do a factory default on access point. So they come back to United States, and then it works.
Okay.
But again, I didn't check recently, so it's just to see if you have seen this issue before or not.
No, but to be honest, I didn't play myself much with country change. As you saw, it was on United States. But I didn't hear that anyone complained so far. I didn't hear that we have like open ticket related to that, but I can check with support, of course, and see.
I can also do some tests here to see if I still have the problem here.
I'll check it here as well.
Yeah.
So in general, nothing can connect with country changed other than United States, right?
Yeah.
Okay.
And the second problem I had was with the SSID.
Yes.
It seems, maybe it's me, but it seems if you rename the Araknis initial, you have some issue.
If you rename the Araknis.
Initial by your own SSID.
Well, this is Araknis initial, for example, I use here.
Yeah, I see. But for installation,
to be honest, I always changed Araknis initial to something else and never had any problem. What kind of problem you noticed? Maybe I simply didn't notice it.
Device didn't connect it.
Okay.
Or device connect, but it seems the connection process didn't go to the end because we had a message on the device saying wrong password.
I think maybe it's related to something else. Because maybe something else, because definitely I know this for sure because I never leave Araknis initial on my SSIDs and never had problem with connection. So definitely it shouldn't be related to the name. Maybe it's something else then. I can guarantee this 100%.
Yeah. I don't know the symbols. Okay, because
maybe
what I
didn't try. To be honest, I didn't try any symbols. Maybe I can try that and test to see.
Yeah. Okay.
Okay. Anything else?
No. That's just two main problem I got.
Okay, I changed the country now. Let me just try to connect from my phone to this SSID. And it works.
It works on your case?
Yeah, it works.
I will do some tests here because, as I told you, I didn't do the test recently.
Okay, just let me know. Let me know if you have problem on your side because
sure.
I just tested and it's fine.
Yeah. Okay.
Maybe Fabrice, the name of the SSID has any special character?
Yeah, that Fabrice mentioned.
No, nothing.
No?
Nothing. No. So what I do or said my partner to do is added a second SSID, put a password, and then disable the Araknis initial. And it works like that. So I didn't investigate deeper,
further.
It worked like this, or I use this procedure, but it's just to know if you have some.
And what access point is in question? 520 or 820 or some older X10?
I had the case with the old one, the 10 series,
10, okay.
and also with the 20 series.
You had the same with both?
Yeah, with 20 series, but
okay.
The last time maybe was in January or February, I don't know.
Okay, just let me know about the current situation, and if you still notice the bug, I'll check. I will do some tests with our developers, to confirm.
I have some products here, and I will do some tests.
Okay.
Yeah, the other bug that I found is when you change the name of the access point in the local UI, and you put a special character, like in Spain we have this N with the sign. Or other special character, the access point cannot connect. You cannot connect to the one.
It cannot recognize. Okay.
Added to oversee, it cannot be added to other oversee.
Yeah. Other improvement we can get on oversee. Maybe get a place somewhere to change the password of all Araknis equipment. Because if
you mean to change the password on the device itself, not on SSID?
No, the password on the device itself, because you can do the configuration of over oversee, and most of the time the partner didn't go on the local device, the switches, the router. Router is a little bit special, but the switches, the access point, so it stays with the default passwords.
No, it cannot stay with the latest firmware. It has to be changed with initial login now. Because when you try initially to log in, you have to change it. It cannot be default anymore.
Yeah, when you connect the first time on the access point. But look, partner goes on oversee, do the configuration over oversee, so they didn't connect.
It didn't connect at all to the direct to UI.
So when you come back 6 months later, or sometimes
I get the point. It is still with default
coming inside.
Since
there is no passwords or default password on the switches or access point, and it changed it. which
I
is
see,
a
I see, I see, I see, I see.
It's not supposed to have access to this product.
Yeah, because for OVRC, you do not need to define any credentials. It just connects without any authentication. So from OVRC, you do not need to change it at all. So
Yeah.
it can still be with default, even if it is fully configured through
Exactly.
OVRC. I understand.
So when you do the configuration, maybe on the dashboard, having a default password.
Set up the password.
Exactly. And apply it to every device you had on OVRC on this installation.
Okay, just to check options we have here on the device configure. Yeah, not much here, definitely.
No.
Yeah. Okay, I understand your point. I agree. That would be a useful feature, definitely.
And for me, it's a security issue. Eh?
Yes, yes, yes. Because locally it is still not configured on the local web GUI.
Exactly.
Yeah. Okay.
And just to understand, when OVRC do the configuration, you have a special access to the different product, a special account made on the access point or switches.
It has like a backdoor access.
Yeah. Okay.
It's not like admin or some additional user. It uses specific port, and it has like a OVRC agent built in which communicates, like a VPN client to say like that. Yeah.
Okay. Good.
Yes.
Okay. Anything else?
I would like to ask you about the images that you used. Was taken from the PCNA, right?
Yes, correct. Yeah.
And I was having a look to the PCNA.
It is changed now. It is moved
Yes.
completely to Araknis. Yeah.
And how can I access? Can I access even if I'm done the old one to the new one to have a look to the content and review it?
Well, you should have, even when you pass PCNA, I think you should still have it on your education account. You should still have access to PCNA course, right? Is it?
Yes.
But I'm not sure. Is it now just updated? So when you open it, you get Araknis, or it's not working, or it is still showing package there?
It
It's showing package.
It shows Araknis,
Okay.
but the content is not updated. For example,
if it is on Araknis, that means it's updated, no?
Yeah, but
you
I know
don't have the last product. You don't have the
520 access point, the Wi-Fi management.
I see. Well, I'm not sure because I didn't check PCNA for a long time. I'm not sure is it included at all on the latest PCNA. Probably not still.
We received a new letter that says that
it's included.
Yes.
Okay, so your own access, your access to the course you have is still not updated with the latest 520.
Yes.
Okay, I have to check that with the education team to see what's going on.
Just to take advantage of the
just to be up to date. Yeah.
Exactly.
Yeah. Okay.
Perfect. Well, that's all for me.
Oscar, anything from you?